Welcome back to the second part of this video. So in this video, I'm going to show you how to actually conduct the correlation regression. Now in Excel, we're just going to do one procedure that'll give us both the correlation and the regression numbers. So we won't be doing two separate analyses. It'll be one analysis that gives us the combined output. I don't think we need to waste any time, so let's jump right back into our example. And so if you didn't save your spreadsheet from before, you can download a new one right below, and then also you can open up that Word document as well that gives us the directions. Otherwise, we're just going to continue from where we left off in the last video. All right, so if you remember from the last video, we were looking at absences and grades, and in this case, do absences predict grades students have in the course? We made a scatter plot, and we saw overall that there was a bit of a negative trend in the data itself. We also checked our assumptions, so for normality as well as for equal variance and also for linear relationship. So in this video, we're going to analyze our data. So go ahead and go to your directions page. So we're on step 4 here. So we'll go data analysis. We'll click on regression, then OK. Then we need to highlight the variable that we've identified as the criterion or the outcome variable. Remember in the last video, we said that was grades. That's what we're interested in measuring or interested in predicting. We're then going to highlight the X variable range, and so this would be your predictor. In this case, our predictor is absences. We want to know, do absences predict grades? So absences is going to be our predictor. We'll check the labels box because we'll have the labels in the very first row, and then we'll put our output someplace in our spreadsheet. Okay, so let's go to our spreadsheet. Let's conduct the analysis. We're going to go to data analysis. I'll look in the list here for regression, and I'll click OK. And then I'm going to input my data. Notice it's going to ask for the criterion first. So in this case, we said the criterion was grades. So you'll be tempted to click on the C column and highlight the entire column. You don't want to do that here. There's another glitch in Excel that it won't allow you to run the analysis if you select the entire column. So you're actually going to have to physically select the data. So I'm just going to left click on my label and I'll drag down and I'll stop where the data stops. So again, don't click on the B column for the row. You actually have to highlight that data. It takes a little bit longer, but it's not that much of an inconvenience. All right, then we need to identify our predictor. So again, we want to predict grades by absences. That's what we're interested in. That's going to go on our x-axis. We're going to do the same thing. So again, don't select the entire column, but rather left click, hold on your label, and drag down and highlight all the values for absences. So really important that you don't click on the columns there. If you do, you're going to get an error, and it's going to be really annoying. It actually makes a really annoying ding at the same time. So make sure to remember to actually manually select your data with the labels. Now we did select those labels. I'm going to check on that box for labels. Notice that we do have a box for confidence level. If we wanted to get the confidence interval for our parameters, we would check that box, but we're going to save that for a more advanced course. Notice you have some other options as well when it comes to residuals and normal probability. Again, in a more advanced class, you would care about those. Those are used to see if we meet additional assumptions. We're not going to worry about that in an introductory course. Go ahead and click output, and then let's place our output someplace in our spreadsheet. Let's place it away from our scatter plot and descriptives just so that we can see it clearly. It looks like I'm going to put it in, looks like cell H17. Then we're going to click OK. And so then you're going to get your output. And in this output, you're going to see that there's a summary output. There is an ANOVA output. And then you're also going to see your parameters output. So let's first take a look at the summary output. So the first thing you're going to notice is that you're going to have this multiple R. This is your correlation value. This is your R statistic. Now, the problem with this R statistic is it doesn't tell you when it's negative or when it's positive. So you need to know when this value should be a negative R or a positive R. And that has to deal with the trend of the data. And there's two places that you can determine whether you have a positive or a negative correlation or an R statistic. You could go up and look at your scatter plot. And if the trend is clear enough in the scatter plot, you may be able to determine that you have a negative relationship here. So again, a negative correlation or a negative relationship is when as absences increase, the other variable decreases. In this case, grade tends to decrease. And that's what we see here. If it was a positive correlation or a positive relationship, then as absences increase, we would expect grades to increase as well. Additionally, if absences were decreasing, we would expect grades to decrease as well. So they'd be going in the same direction. But here they're going in opposite directions. Absences are increasing, grades are decreasing. So that means that this value should be a negative 0.75. I'm just going to put that to the side here just so I don't get accidentally confused. I do have a negative relationship, a negative correlation, and that value for that R statistic, for that correlation statistic is negative 0.75. Next, you're going to see the R squared value. This is your effect size. So you don't need to calculate an effect size here. It's given to you in the output. Now it works just like the effect size in the last module, in module number 5. It's an R squared value. We can turn that into a percent. We can say it looks like 56% of the variance or differences in students' course grades can be accounted for by the number of absences. That's going to be a very large effect size. Now you should note that because both of our variables are now continuous, what we determine as small, medium, and large are going to change. So I'm just going to write those conventions to the side here. So we have no effect, we have small effect, we have medium or moderate effect, and then we have a large effect size. A no effect would be around 0. A small effect would be plus or minus 0.01. A medium effect would be plus or minus 0.09. And a large effect for that R squared value would be plus or minus 0.25. And so I'll just label those effect size conventions for R squared. Now, if you didn't want to use R squared to compare that effect size, you can use the R, the correlation value. If that was the case, you would just unsquare all those values. So if you're using the R statistic instead of the R squared value, I'll put R stat here, then those cutoffs would still be 0. It would be plus or minus 0.1, plus or minus 0.3, and plus or minus 0.5. But note that the relationship between R and R squared is that R squared is just the R value, the correlation value squared. So that means with our conventions, if we were to square 0.1, we would get 0.01. If we were to square 0.3, we would get 0.09. And if we were to square 0.5, we would get plus or minus 0.25. And so whether you use R or you use R squared, you should be able to determine whether you have a small, medium, or large effect. Just make sure that you're using the right conventions given the value that you're comparing. So if I'm looking at my R squared value, I get 0.55. So I want to make sure I compare that to my R squared conventions. In this case, it looks like I have a large effect, as 0.55 or 0.56, I guess if I'm rounding to 2 places, is closest to my large category than it is to any other category. Note that if you were to use the R value, the correlation value of 0.75, that also would still be categorized as large, and we would compare it to the plus or minus 0.5. It doesn't matter which convention you use, just as long as you are consistent in your comparison. So next in that regression output, you're going to notice that there's an adjusted R squared. We're not going to worry about that in this class, but realize that we can get another measure for that effect size that corrects for the number of observations we have, as well as the number of variables we have. And so if you were to take a multiple regression course, you would care more about that particular value. Here, because it's simple linear regression and it's an introductory course, we're not going to worry about that adjusted R squared. Next, you're going to see a standard error. That standard error is the standard error of the estimate. That is a value that you will want to report. So I'm going to come back to that standard error of the estimate here once we talk about our regression equation. But essentially, it's a measure of error for any one single prediction for an individual. So before we go any further, we need to determine whether or not we are going to reject the null hypothesis. In other words, is there some sort of predictable relationship between these two variables? So we have the R statistic, We know it's a negative 0.75. But what we don't know is what's the critical value. At what point are we going to say that that R statistic is large enough for us to reject the null hypothesis? That means we need an R critical value. For that R critical value, we need to know if we have a one or a two-tailed test. So remember, if you go to your code book and you look at that scenario, we already indicated in the last video that we have a one-tailed test here. We expect a negative correlation. So that means when it comes to the R distribution, we don't need to look in both tails. We can set up our critical region in just one of those tails. I'm going to give myself a little bit of space here. I'm going to draw on the spreadsheet. I'm going to put that distribution up here. So remember that R distribution is a normal distribution. It looks like the T distribution is still centered at 0, so R equals 0. But what is different about this distribution is that it actually touches the x-axis at 2 points at -1 and 1. And so if you have a correlation or an R statistic that's greater than 1 or less than -1, then you've done something horribly, horribly wrong. So what we want to do here is we want to create some regions in this distribution where we're going to reject the null hypothesis. If we get an R statistic that falls between those two regions, we're going to fail to reject. We're going to say that there's no relationship between the variables. But if we reject a null, we're saying that there's some predictable relationship between these two variables. So we need that R critical value. And you're going to find that in your table. So this is the tables in the back of the book, or you can go online in the module and select the link that has a table for the R statistic. So let's go to that table. The table you're looking for is going to be the Pearson correlation coefficient table. And I'll just move it to the side here a little bit so you can see it. Now the Pearson correlation coefficient is the R statistic, so it doesn't say that up there, but that's what it is. You're going to notice two overall sets of columns. One is for a one-tailed test, the other one's for a two-tailed test. Now each of these larger columns are going to have 3 columns underneath it. One is for the degrees of freedom. The other one are for critical values at an alpha of 0.05, and then another one at an alpha of 0.01. So in this case, we said that we had a one-tailed test. So we're going to be looking at the one-tailed test critical values. We need to determine what our degrees of freedom are. We already know that our alpha is 0.05, and you should note here a couple corrections in this table, and the one that I give you for the exam will have these corrections in it. But it's not capital N here. Capital N is total number of values in your data set. It's actually lowercase n, the number of observations in one of your groups, so not both of your groups combined. And then the other thing too here, you're going to see that there's this, it says the alpha is 0.005. That's a typo. It should only be 10 there. That is an alpha of 0.05. You'll have those corrections on the table that you need for the exam, but just remember those two things as you're looking up your critical values. Okay, so we need to know our degrees of freedom. So how many values are free to vary infinitely? And it's going to be lowercase n minus 2. I need to find out how many observations are in one of my groups. So in other words, the count in one of my groups. And I'm going to find that in my descriptive statistics. In this case, right here, notice that we have a 78. And so we're going to use that as our n. So 78 minus 2 is going to give us 76. So we're going to look for 76 in our table. Now, once we get to larger numbers, we're not going to have every single value that's there, but we'll go to the one that is closest to. So as I scroll down on this first page, notice it stops at 60. So we're going to continue to the next page. We have 76, so we're going to round that up to 80. So it looks like the row we're interested in is this one right here. So remember, it's a one-tailed test. We have about 80 degrees of freedom. And then we have 2 columns. We have one for alpha of 0.05, another one for alpha of 0.01. We want the 0.05. So it looks like the value we're going to get is 0.18. Now, again, this table does not tell you when it's negative. You need to know when it's negative. In this case, we have previous research that's telling us to expect that our correlation should be a negative correlation. So this is going to be a negative 0.18. And so I'll put that here on my distribution. So an R of negative 0.18. So taking a look at our data, and we already know this because we calculated that R statistic earlier, we have an R statistic of negative 0.75. So again, that critical value is negative 0.18. We exceed negative 0.18 here. If I was to put this on my distribution, it'd be someplace right about here. That's going to be in our reject the null region. We're going to reject the null hypothesis. It appears that there is a relationship between grades and absences. And if we reject the null in a correlation, what we're saying is that that relationship is predictable. So we can say that it appears that the number of absences students have in a statistics course predicts the grade that they're going to get in that particular course. So when we reject the null hypothesis, that tells us that we can continue on to a regression. If we were to fail to reject the null hypothesis, we'd be saying there's no relationship between the variables. And if there's no relationship, then there's no reason to go do a regression to try to determine what that predictive relationship is like. So again, we only continue on if we reject the null hypothesis with the correlation. Now that should sound familiar. We did that with the F test. Remember with the post hoc test, if we rejected the null, we did post hoc test. Failed to reject, we didn't do post hoc test. The idea is similar here. If we reject the null with the correlation, then we'll continue to the regression. If we fail to reject with the correlation, then there's no reason to look at the output for the regression. So now that we've determined that there is a predictable relationship between grades and absences, let's go ahead and go down to those last two outputs. The first box you see for output is your ANOVA output. I'm going to come back to that here in just a second. But really all this ANOVA output is doing is measuring the same thing as our correlation. So it's telling us whether or not the correlation is significant, if there's a relationship, a predictable relationship. And you'll notice that in this ANOVA table, that looks very similar to what we did in the last module. We divide our mean squared between, in this case, we call it regression, divided by our mean squared within, which we call residual. And that gives us an F statistic of 95.12. It's a very high F, and in this case, we would reject the null hypothesis if we were to look up an F critical on an F statistics table. But what I want to look at now is the coefficient output that's right below. And so notice here that we have two rows of data. One is for absences, and the other one's called absences. The one that has absences in it, that's going to be your predictor. And so you always want to make sure that you've entered your data correctly. And if you've entered your data correctly, then you're going to see that absences should be here. So if grades was here, then we'd be worried that we put in our variables in the wrong boxes, because your criterion should not show up in this output. Okay, so then we're going to notice that we have a column for coefficients. We have a column for standard error. Make sure you do not confuse this standard error with the standard error of the estimate. Those are two different things. So make sure you're reporting the standard error of the estimate, which is up here in your summary box, not down here in your parameters box. Then you're going to notice some T statistics. And so what's interesting about this is that now we have a T statistic, we have an F statistic, and up here we have the R statistic. So we have three of the things we've learned in this class all in this particular output. And I talked about this at the beginning of the semester, that all of our formulas are related to each other, that we can go from T to F and F to R and R to T quite easily. It's just a mathematical conversion. So just to demonstrate here really quick, I'm going to put those formulas on here so you can see that particular relationship. So remember we learned in module 5 that F equals T squared. In other words, T equals the square root of F. If I wanted to get my R statistic from F, R equals the square root of F divided by F plus the degrees of freedom. If I want to get R from T, it would be R equals the square root of T squared over T squared plus the degrees of freedom. And so notice that we can go from T to R to F to T to F quite easily. All three of them are related to each other. So when we look at this regression output, we cover three of the statistical tests that we learned this semester. And in fact, the correlation itself, the R value, is a standardized value that uses z-scores. And so essentially, the regression itself ties together everything we learned this semester into one module. And that's why it's a great way to end the semester. It's a great review over everything that we've learned this entire course. All right, so let's get back to our parameter estimates and this output here at the bottom. You'll notice there's a few things that are in here. So when we conduct our regression analysis, our whole purpose is to be able to create a regression equation that we can use to predict for an individual. So this regression equation, as you learned in the narrated PowerPoint, is y hat equals a plus bx, where a is the constant, which by the way you can find right here. It is the intercept coefficient, and b is the slope, and the slope happens to be right here under our coefficients for our predictor of absences. Now when it comes to this equation, we can add the error term as well, which would be plus the standard error of the estimate, which that value is right here. So be able to fill in your regression equation. If we were to write this out, we would say y hat equals 94.88 minus, and it's a minus again because our coefficient is a negative value. Remember, we have a negative relationship. So I mentioned earlier how to tell if your R statistic was positive or negative. One way is to look at their scatter plot. The other way is to look at the sign of your coefficient for that predictor. Here it's a negative value. So that tells us we have a negative relationship. So it's a negative correlation. And so a negative and positive makes a negative. So it's going to be 94.88 minus, if we're rounding to two places, 1 times the number of absences, x, plus and minus, because the standard error of the estimate goes in both directions. So plus and minus the standard error of the estimate of 6.74. And that would be our regression equation. So what we need to do now is talk about each of these components and talk about what it means when it comes to explaining our results. So I just took a moment and cut the video so that you can see that formula typed out. So again, 94.88 minus 1 times x plus or minus 6.74. And again, we got that all from our output. All right, we got it from our coefficients here. And we got it from our standard error up here, the 6.74. Let's talk about each of these values. So we said we had A, we had B, and we had the standard error of the estimate. So let's interpret each of these values. So A again is the intercept, or what we call the constant. Our value that we got here was 94.88. Something to remember is that all these values are in raw terms. When I say 94.88, because we measured course percent, it's going to be in percent. This is really important because when it comes to other different examples, if I measure in feet or as a length, then that means my answers are in feet. If I measured age by years, then my answers are in years. Here we're using percent for a grade, so our answers are going to be in percent. So what I see as a common mistake for students is that they apply percents to every scenario, regardless of what the raw unit is. So here are raw units and percents. We're going to use percents, but make sure you're aware of what your units of measurement are for your particular scenario, either on exam or an assignment. So A is also known as the y-intercept. So what that means is that on my scatter plot, that the y-axis is right here. And so it's where the regression line intercepts the y-axis. So in other words, when absences are 0, when students have perfect attendance, when they haven't missed any courses, what would we expect a student's grade to be? Now, it looks like it's going to be up here in the 90s someplace. Well, that's going to be that value we have for that intercept. So when we interpret the A value here, when we interpret that y-intercept, that constant, what we're saying is that it appears that when a student has 0 absences, we would expect their grade to be a 94.88% on average. Again, remember that it's a percent because we're measuring in percents. Again, if we're measuring feet, it would be in feet, etc. It's always in raw units. All right, so let's talk about B. So B is the slope. So it's the rise over run. If I was to look at my scatter plot, we see that there is a slope. This slope is trending down, so that for every increase in absences, there's a certain decrease in grade. That's exactly what this slope is. So we would say it appears that for every increase in absences, so every one increase in absences, we would expect a student's grade to decrease by 1 percentage point on average. So essentially that's the cost for the absence. So if a student misses class, that student could expect to see a decrease in the grade by 1%. Not because attendance was taken or points are tied to attendance, but because they miss information that's important to their grade. So every absence costs about 1% on average. Some days may be more, some days may be less, but roughly 1% on average. So finally, we have the standard error of the estimate. And so again, that standard error of the estimate is how much we would expect any one prediction to be off. And realize it's really hard to predict for an individual. And so usually the standard error of the estimate is pretty wide. Now we can narrow that standard error of the estimate by adding additional predictors, and we call that multiple regression. So the more predictors we have, the better our prediction is going to be, and that standard error is going to decrease. But here we only have one predictor, so realize that course grades has a lot more to do than just absences, right? It's how much you study, it's your quality of study, it's whether or not you're taking other courses, whether or not you have work outside of the class, so you have the time to commit to a class. There's a lot of variables that goes into how well a student does, and not just one predictor such as absences. So let's take a look at our standard error of the estimate. Notice the value is 6.74. So that means for any one prediction for a student, we would expect to be off by 6.74 percentage points in either direction at a 68% confidence. So our standard error of the estimate, we would say we would expect that any one prediction for course grades based on absences would be off by 6.74 percentage points in either direction on average. And that should make sense because when it comes to predicting for individuals, the distribution is a normal distribution. So I'll draw that out here really quick. And remember, this is going to take you back to Module 2 as well. And so it's centered at the predicted score, y hat. And just like any other normal distribution, we can divide it up by standard errors. And so remember that between a standard error of -1 and 1 is the region which we call average. And so when we subtract a standard error from our predicted value, we're creating a range of where we expect that student's grade to be. And so our best guess is what we get from our prediction equation, but it could be higher or lower than that in reality. And so that standard error of the estimate allows us to create the borders of that particular range for predicting the individual score. And so you may remember also from module number 2 that 34% of the population have values between 0 and -1, and another 34% between 0 and 1. Combine those together and you get 68% of the population. So that's why we say in this particular case that it's at a 68% chance. So let's go ahead and add that to our explanation. At a 68% chance or probability. Okay, so we're almost done here. So let's apply it. So let's say we have Greg, and Greg has 7 absences in the course. Can we get a prediction for Greg and what his grade might be? Well, in order to do that, we're going to plug in 7 into our regression equation. So I'm just going to go to the cell next to Greg's name here. I'm going to plug in his absences into our regression equation. I'm going to equals 94.88. I'm going to subtract my b value for my slope 1 times the number of absences of 7. And notice here with this equation, we don't necessarily need to enter it all in here. 1 times 7 is 7, so we'd just be subtracting 7 from 94.88. But that's okay. I still want to show you the process so that when you have different values, you're still able to do it. And so I'll hit enter here. And so it looks like we predict Greg's grade to be 87.88%. Now remember that is our best guess for Greg's grade. We would say with 7 absences, predict his grade to be 87.88. But that's not going to be his actual grade. His actual grade is either going to be higher than that or it's going to be lower than that. The chance of it's going to be exactly 87.88 are actually pretty slim. And that's where the standard error of the estimate comes in. So remember, in that regression equation, we can add and subtract 6.74 to create a range of where we expect Greg's grade to fall at a 68% chance. So to do that, I'm going to take 87.88 and I'm going to subtract 6.74. Hit enter. And then I'm going to take that same value, I'm going to add 6.74. So now we have a better idea for predicting for Greg. So our best guess with 7 absences is that he's going to have an 87.88%. But when we take into account variability, the fact that it's difficult to predict for individual, his actual grade will probably fall someplace between 81.14 and a 94.92% on average. And that's a pretty wide range. But again, remember, we only have one predictor. Now, that doesn't mean that this predictor is not useful. So even though we get this wide range of what his grade can be at a 68% chance, realize that we still know from the analysis that absences matter at the individual level. We saw that with the effect size. We know it matters at the group level as well because we saw that with the hypothesis test. So we know that absences impacts grade. What's hard for us to say is how it's going to impact grades, let's say for you or for me as an individual. And that's why we get these wide ranges. We know it matters, but how much it matters depends on the individual. All right, so if I was to write this out, we might say that we would predict Greg's grade to be an 87.88%. However, there is a 68% chance that his grade could be anywhere between 81.14% and 94.62%. Now, if we wanted to increase that chance level to a 95% chance of finding his actual true grade, then we would double the standard error of the estimate. So 2 standard error of the estimates away from our prediction would cover 95% of the prediction distribution. And essentially that would just be adding and subtracting another 6.74. So that's it. That's regression in Excel. We've covered a lot of material this semester, including a lot here with just this module and this example right here. So this is the last video. So congratulations, you're almost at the end. We're almost there for this semester to be over. I know it's been a very, very quick semester, and I appreciate all the effort that you put into this course. As you're wrapping up this video, please remember to upload your spreadsheet with your name as the file name and go ahead and submit it below.